Section 16.3, the fundamental theorem for line integrals. So as a review, we remember the fundamental theorem of calculus, and in case we don't, it states that if we have an integral, a definite integral from some a to b of f prime of x, so the derivative of capital F of x dx, that's just equal to the antiderivative evaluated at b minus the antiderivative evaluated at a. And in this example, just a note here that antiderivative generally has the capital F in calculus 1, so f prime of x is just the same as lowercase f of x. So this is our fundamental theorem of calculus. Now we're going to apply this to vectors. Because if we think of the gradient of f as kind of a derivative of f, because if, say, we're in two dimensions, the gradient of f of x and y would just be a vector of the partial derivative of x and the partial derivative of y. So if we can think of this as sort of like a derivative, then we can apply this fundamental theorem of calculus to curves. Because we're saying that if we have the gradient inside of the integral, taking that dot product with dr, which we talked about in section 16.2, then this is kind of like the original function evaluated at r of b minus the original function evaluated at r of a. So kind of like the same thing here. If the gradient is the derivative, we're going back to the original function, sort of taking the antiderivative. And in this case, just note that the initial point is a, the terminal point is b, just like in calculus 1. So let's do an example of this. We want to evaluate this integral of the gradient of f and the dot product of dr, where f of x, y, and z is equal to cosine of pi x plus sine of pi y minus x, y, z, and c is any path that starts at the point 1, 1/2, 2, and ends at 2, 1, -1. And so I know that the fundamental theorem of line integrals tells me that the definite integral of some curve of the dot product of the gradient f and dr is just equal to this original function f evaluated at r of b minus f evaluated at r of a. Now in this case we have the original function, so we have the original function f of x, y, and z of cosine of pi x plus sine of pi y minus x, y, z. So we already have our original function and we want to evaluate this at r of b and r of a. And we're told that it really doesn't matter what this exact path is, just that it starts at 1, 1/2, 2, and it ends at 2, 1, -1. And so this is going to be our a, and this point is going to be our b. And so we're just going to find f of a and f of b. And so finding f of b, we're really finding f of 2, 1, -1, which is just going to be cosine of 2 pi plus sine of 1 pi minus 2 times 1 times -1. And this is going to give us cosine of 2 pi is 1, sine of pi is 0, 2 times 1 times -1 is -2, so this is going to be a 3. Now our function evaluated at this first point, because we're taking the second point and subtracting the first point. So at the first point, this is f of 1, 1/2, and 2. Plugging this in, we get the cosine of 1 pi plus the sine of pi over 2 plus 1 times 1/2 times 2. Simplifying this gives us the cosine of pi, which is -1, plus the sine of pi over 2, which is a +1, plus 1 times 1/2 times 2. I'm sorry, this is supposed to be a minus, which will give us a -1. And so we're left with -1. So finally, this fundamental theorem of line integrals tells us that we're just taking this function evaluated at the terminal point, subtracting the function evaluated at the initial point, and we get 3 minus -1, which is equal to 4. So this is what we get for that integral. Something to note here is that when we took the dot product of the gradient of f and dr, we didn't even need to find the gradient because of this theorem. And another important thing here is that it doesn't matter what path we take. This theorem, you could say, is path independent. And this is the same from the fundamental theorem of calculus that you learned in Calculus 1. A good way to look at this is in the form of vector fields, where it doesn't matter what path we take. And for our application problem here in physics, we talk about work, which is just the dot product of force times displacement, is also path independent. So now let's just talk about a few definitions. So if f is a continuous vector field in some domain D, then we have this definition of a conservative vector field. And we brought this up in the last section, but now we're really going to talk about it. We said that a vector field is conservative if there exists a function f such that f is equal to the gradient of f. This function is called a potential function of the vector field. So what that means is that if we can find a function that is the original function that gives us a certain gradient of this vector that we're given, we're going to do an example of this. We talked about the fact that this integral of the dot product of f and dr is independent for any point c1 and c2, as long as we have the same terminal and beginning point here. Then we just have a few more definitions that a path is called closed if its initial and final points are on the same point. And so let's look at this example. We have a simple closed region because we'll start at one point, go all the way around this region, and end up back at the same point. So this is closed. It's called simple if it doesn't cross itself. So we've got simple and not simple. This one crosses itself. It's called open if it doesn't contain any of its boundary points. So it's essentially open if it's not a closed surface, a closed region. It's connected if we can connect any 2 points in a region with a path that lies completely in DD. If we look at all of these examples on the right-hand side, we can say that they're certainly connected because at least these two are connected, because if I draw a point here and a point here, well, I can connect this with a path that lies within this region. But if I have a point here and a point here, then there's no way I can connect these while remaining in this region. So this one is actually not connected in general. And then as far as simply connected goes, it's just simply connected if it's connected and contains no holes. Pretty straightforward there. All right. So just to summarize, we said that the integral of this curve of the gradient of f and the dot product of dr is independent of path. All right, we covered this. We said it doesn't matter what the path is. Then we have if f is a conservative vector field, then the integral of f and the dot product with dr is independent of path. Now remember what if it's a conservative vector field, then this is independent of path. Remember what conservative means. Conservative means that we can find some f that is equal to the gradient of f. Again, we're going to do an example of this. If f is continuous in an open connected region of D, and if this is independent of path, then f is conservative. So we just have this going the other way around. These are just converse statements. Finally, we have this idea that if this is independent of path, so if this is a conservative vector field, then the integral of the dot product of f and dr is equal to 0 for every closed path C. And let's again relate this back to work. I mean, work is just the easiest application to kind of look at and work with if you're familiar with it. So for work, if we have a displacement of 0, then work is equal to 0. Meaning if, according to physics, when we're talking about work, if I'm sitting down in a chair and I stand up 20 times and then end up sitting back down in my chair, no work is accomplished. And so we can view this in vector fields, because if I have a closed path, that means I'm starting where I'm ending, my terminal point and my initial point are the same. So this is just going to give us 0. So now to determine if the vector field is conservative, because if the vector field is conservative, then we can say that the integral of the gradient of f and dr is equal to the integral of f and dr. So this is going to be important if it's conservative. And so to find out if it's conservative, all we're doing is we're finding the partial derivative of p with respect to y and the partial derivative of q with respect to x, seeing if they're the same. Because if the partial of p with respect to y is equal to the partial of q with respect to x, then I can find some function that will give me a gradient of this. So in example 2, we want to determine whether or not the vector field is conservative. We've got f of xy is equal to x minus yi. And so this is our p plus x minus 2j. So this is our q. Then all we're doing is we're seeing if the partial of p with respect to y is equal to the partial of q with respect to x. So is this true? Well, let's find the partial of p with respect to y. Simple derivative here. This just gives us a -1. And the partial of q with respect to x. Derivative of x minus 2 with respect to x is a +1. Because -1 obviously does not equal +1, then the vector field is not conservative. Okay, let's do one more example. Let's determine whether this is conservative or not. Well, this 3 plus 2xy is our p. This x squared minus 3y squared is our q. So let's find the partial of p with respect to y. And this is going to be just a 2x. And our partial of q with respect to x is going to be 2x minus 0, so again 2x. And because, yes, 2x is equal to 2x, which means these partial derivatives are the same, then we can determine that yes, this vector field is conservative. So once a vector field is conservative, then we can find this potential function. Now, in chapter 14, we introduced gradients, and we know that it's pretty easy to find the gradient of a function. We're just taking the partial with respect to x, the partial with respect to x as the component attached to our I, and the partial with respect to y as the component attached to our j. But the question is, how do we get from the gradient to the original function? And this is our method. So if we know that a vector field is conservative, and again, all this really means is that the vector field, which is a capital of F, so this is our vector field, is the gradient of F. So is the gradient of some scalar, so just non-vector scalar function. So if this is true, the vector field is conservative, and we can go from starting off with this gradient to the original function. All right, so that's going to be our first step, determining if it's conservative. If not, then we can't do this process. We can't find the potential function. Then, just remembering that P is just the partial with respect to x and Q is the partial with respect to y, we want to find f of xy. Because, for example, P is the partial with respect to x, to find this original function, we can just take that antiderivative or the integral, because this is the derivative with respect to x. Now, when we integrate, we're going to have this constant of integration, because this does not take into consideration any constants we may have had. And in this case, our constant, the value of c, is just going to be equal to either g of y, or in the case of three variables, g of y comma z. Now, if we have to do this again, there might be another constant of integration, and we may have to go to some constant of integration called h of z. And again, we'll do some examples of this, allowing us to find our potential function. So example 4, if f of xy is equal to the quantity 3 plus 2xyi plus x squared minus 3y squared j, find the function f such that the vector field f is equal to the gradient of f. Now step 1, we need to find if this is conservative. And yes, it's conservative because this was the exact same question in problem 3. Step 2, we're finding the original function. And I'm just going to keep doing this the same way. In our process, we've got options, but I'm always just going to use P because it doesn't matter, and I think it's, easier for the most part. And so I know that P is equal to 3 plus 2xy. All right, because this is a gradient, I know that this is f of xy. This is the partial derivative with respect to x and y. So our partial derivative with respect to x is 3 plus 2xy. Now if this is the partial with respect to x, how can I get to the initial function? Well, I can integrate this. So I can integrate 3 plus 2xy with respect to x. So in this step, we are integrating that partial with respect to x with respect to x. Okay, so let's integrate. With respect to x, this is going to become a 3x. 2xy is going to become a 2 over 2x squared y, so just x squared y. And then we have our constant of integration. Now, let's think about the fact that this is with respect to x. If I have a constant of integration, I know that that can either come from constants or it can come from any other y terms. Because remember, with respect to x, I'm treating y as a constant. And so instead of calling this c, I'm going to call this g of y. And again, this is my constant of integration. And so because this is the original function, taking the integral of a derivative brings us to the original function. Well, now I can solve for this constant of integration by taking the partial derivative with respect to y. The partial with respect to y is just going to be 0 plus x squared. Plus, because this is a function of y, I can write this as g prime of y. Now remembering that q is equal to x squared minus 3y squared. Well, my q is really just the partial with respect to y. I'm now using this idea to solve for my g prime of y. And so if x squared plus g prime of y must be equal to this q, so x squared minus 3y squared, then I can come to the conclusion that g prime of y must be a negative 3y squared. And if this is the case, remembering what I want this original function. So my goal is to get back to this original function. I need g of y. Well, if I have g prime of y, I can find g of y by just taking the antiderivative of this and the integral of negative 3y squared, or the antiderivative, is just going to be negative 3 over 3 y cubed plus another constant of integration. Now the only thing left to do is put this all together, because we want to find this function f. So we're looking for this function f, and we can write it as f of xy just because it's a function of x and y. We've got this constant of integration g of y, and so we can just write the function f of xy is equal to 3x plus x squared y plus, and then we found out that this constant of g of y was a negative y cubed plus c. Now, these instructions just tell us to find a function f, and the reason is because no matter what constant we put on the end of this, this will still be a potential function. And so for a function of f, any function of f, let's just let c be equal to 0. So we can write our final function as f of xy is equal to 3x plus x squared y minus y cubed. So this is our final function, and this is just something you're going to see happen regularly, where we just end up dropping this constant at the end because a perfectly fine example of this function would be with a constant of 0. All right, so in summary, our first step was to find out if this thing is conservative. If it is, we can continue. Step two was just figuring out that this p was just attached to the I. So step 2 and step 3 are kind of the same thing. Step 3 was to integrate this function, this partial derivative with respect to x to get back to the original function. So this was step 3. And then step 4 was solving for this constant, g of y, by taking the partial derivative with respect to y. So this is step 4. And finally, step 5 was just finding one of these potential functions by assigning a value to a constant. We're always just going to choose 0. So this is our procedure. Now, the same thing would have happened if we had taken this q, taken the partial derivative with respect, taken the integral of this with respect to y instead of x. We could do the same thing here. So this is why our instructions kind of contain these options. We don't need to use this first expression. However, it's generally just easier to follow this procedure and work our way from left to right to keep ourselves organized. At least that's what I've found. So now part B asks us to evaluate this line integral where c is the curve given by r of t is equal to e of t to this times sine of ti plus e to the t cosine of tj as t goes from 0 to pi. And remember, if we said this is conservative, then we have proven that the integral of the dot product of f and dr is equal to the integral of the gradient of f and dr. And because of this fundamental theorem of line integrals, this is equal to f of r of b, starting with our terminal point, minus f of r of a. And so remembering that from part A, we found what this function is. F of xy is equal to 3x plus x squared y minus y cubed. And so now we can just start to find r of b and r of a. And in this case, our a is that first point and our b is that terminal point. And so we can find r of b by finding r of pi, which is equal to e to the power of pi sine of pi I plus e to the power of pi cosine of pi j. And the sine of pi is 0, and so this is going to just be 0i. And the cosine of pi is -1, so this is going to be a minus e to the power of pi j. And I can also write this just as 0 and a negative e to the pi. All right, so for our initial point, our r of 0 is just e to the 0 times the sine of 0 I plus e to the 0 times the cosine of 0 j. Sine of 0 is 0, so we're going to be left with 0i. The cosine of 0 is 1, e to the power of 0 is 1, and so we're going to be left with 1j. So I can write this as 0, 1. And so I've just got f of r of pi, which really means f of 0, e, negative e to the pi, minus f of r of 0, which is f of 0, 1. And f of 0, negative e to the pi, is just going to be 3x, which is 0, plus x squared y, well x is 0, so that term's just going to be 0, minus y cubed. And a negative e to the pi cubed, well, this is going to still be a negative times a negative, which is a positive e to the power of pi. Our f of 0, 1 is just going to be plugging into this function. 3 times 0 is 0, plus 0 squared times 1 is 0, minus 1 cubed. So this is just going to be a negative 1. And finally, we get e to the pi minus a negative 1, which is e to the power of pi plus 1. And so this is our solution. Now, just to point out, we could do this without this new theorem. We could do this without the fundamental theorem of line integrals. So without the fundamental theorem of line integrals, because we know that our original function f, that vector field, was given to be 3 plus 2xyi plus x squared minus 3y squared j. Is it 3 minus 2xyi plus x squared minus 3y squared j. Okay, this is just a plus. And we can also find dr. We can really find r prime of t. And our r prime of t is going to be, well, e to the t sine of ti. So taking that derivative, we get e to the t times the cosine of t plus sine of t times e to the t, just using that product rule. So that's our I component. And then our j component would be, again using the product rule, a negative e to the t sine of t plus e to the t cosine of t, j. And then we would just take the dot product. And so what we would be doing here is we would be finding f of r of t dot r prime of t dt. And so to find f of r of t, we would just be plugging e to the t sine of t in wherever we see x. We would be plugging e to the t cosine of t wherever we see j. And so we could see that this could just get complicated. And so without using the fundamental theorem of line integrals, this just gets much more complicated. And so this is just to show that this theorem is just kind of a shortcut. We can do this without the fundamental theorem of line integrals. In fact, we can always solve these types of problems without this theorem. However, this just makes our lives a whole lot easier. It's kind of like in Calculus 1 when we had the limit definition of the derivative, and then we introduced the power rule. Given that f is conservative and f of x, y, and z is equal to 2xy cubed z to the fourth I plus 3x squared y squared z to the fourth j plus 4x squared y cubed z cubed k, find a function f such that the gradient of f is equal to that vector field. And so, let's start off, and we're just going to start off our process with this partial with respect to x. I'll always start here and just go from left to right. I think that's the best way to go about it. And so I will start off with the fact that the partial with respect to x of this function x, y, and z is just equal to 2xy cubed z to the fourth And to find that initial function, I can take the integral of 2x y cubed z to the fourth with respect to x. And so this will give me that initial function. When I take the antiderivative with respect to x, this just leaves me with x squared y cubed z to the fourth power. Of course, I've got my constant of integration, and in this case, because when I take the integral with respect to x, I'm treating y and z as constants because I've got these three variables, I'm just going to call this constant g of y comma z. So now I'm solving for this g of y comma z. So my next step is to solve for this constant. And so I'm going to take the partial derivative with respect to y so I can compare it to what I have here. So the partial with respect to y of x, y, and z, treating x and z as constants, I am left with 3 x squared y squared z to the fourth plus g prime of y and z. And so now I'm comparing this to my partial with respect to y in the initial problem, which was 3x squared y squared z to the fourth power. Because I see what I see in this potential function with respect to y, as I do in the initial problem, this tells me that g prime of y and z is just 0. So I've successfully solved for g prime of y and z. What that means is that g of y and z is just a constant. And so finally we've got this z to deal with because we haven't yet looked at the partial derivative with respect to z. And so let's go back to this initial function, f of x, y, and z. And let's find the partial with respect to z. The partial with respect to z, treating x and y as constants, is going to be 4 x squared y cubed z cubed plus my final constant. And because we've dealt with the y, we've looked at our partial with respect to y, we're just left with a potential constant with respect to z, and so I'm going to call that h of z. Rather h prime of z because this is the partial derivative. And so let's compare this now to our partial with respect to z from the original problem. Because our partial with respect to z from the original problem is 4x squared y cubed z cubed. This is exactly what I see here, and now I can conclude that h prime of z is just equal to 0. Which means that my original g of yz is a constant and my original h of z is also a constant. And so we are just left with f of xyz being equal to x squared y cubed z to the fourth plus, and I'll just call this the fact that g of y and z is equal to some constant c. And I'll call this original h of z equal to a constant k, just so we can see what happens here. So this is going to look like a plus that constant plus that other constant. And so one potential function is just going to be the situation in which both of these constants are 0. So I can say that f of x, y, and z is equal to just x squared y cubed z to the fourth power. And I can just look back at this original f of x, y, and z, I can look at this gradient, this vector field really, just to confirm that this is true. So is the partial with respect to x 2xy cubed z to the fourth? Yep. Is the partial with respect to y 3x squared y squared z to the fourth? Yes. And then the same with the partial with respect to z being 4x squared y cubed z to the fourth. So I can see that this is our potential function. And that is it for the fundamental theorem of line integrals.